today's topic you can note down. It is properties of fluid and basic definitions of fluids we are going to cover in today's lecture. So whether PPT is visible to you?
Yes, sir.
Sir.
Okay. So as a generally, right, when you will ask somebody, right, who doesn't know ABCD of this subject, and if you say that what is a fluid, and his obvious answer will be something, he will say fluid is something called liquid. But in reality, it's not liquid. It is something which is having a inherent property of flowing. Now, what all things can be flow, right? Liquids can flow, gases can also flow, right? But solid cannot flow. So solid, you can remove gases and the liquid. Both can be considered as a fluid because fluid means it will flow because the term came from the flow. So it is having inherent ability of flowing. So that is known as fluids. So when we talk about fluid mechanics, mechanics means it is some sort of science, right, which is dealing with the study of certain substance. So when it is going to relate with fluid, right, when we are writing fluid mechanics, so we can say it is a branch of science that deals with the properties of fluid, or you can say behavior of fluids, namely liquids or gases, either at rest or in motion. All right, it may be at rest if you are filling the liquid or gas within a closed container, then molecules may still be vibrating at their own position, but they may not be moving. So we can consider the fluid at rest in that condition if you are leaving the fluid right in open space. Why? Due to the density gradients, due to the pressure gradient, fluid starts moving. So in that case, what will happen? All the molecules of fluids will also be moving, right, with respect to each other. So that kind of motion is then motion will start. When motion is going to start, and now you are want to finding out why it is happening. Then you have to measure the velocity of that fluid domain, at what velocity it is going. When based on velocity, you will predict the force, right? What was the force that was applied? Because of that, we got this velocity. So then those all three equations will come into the picture, right? Continuity equation. Then we apply the momentum equation to get the force. All right. If you want to know what is the energy of fluid, right, by which it is moving, then you will be applying the Bernoulli's principle, that Bernoulli's equation or energy equation, to come at the conclusion that this is the amount of energy that fluid is carrying away. So that is, that will come in the third unit, but as I generally I'm saying, so we can study the fluid either at rest or in motion. And now, there are three branches of, this fluid mechanics, right? When you are studying the fluids at rest, that kind of study is known as fluid statics, right? And the branch of science which is dealing with the fluid motion, when we are not considering any pressure force causing that motion, such kind of study is known as kinematics. So kinematics is the branch which deals with the fluid motion, but is not considering the pressure force which has this motion, which causes this motion. Such kind of study is known as fluid kinematics. There is another branch that is called fluid dynamics. When dynamics comes into the picture, that means you are providing the momentum to the fluid. How will you provide the momentum? By applying the force. So dynamics is the branch of science that deals with the fluid motion when considering the pressure forces also, right, causing that motion. Such kind of studies known as fluid dynamics, right? So these are the three sub branches of fluid mechanics, namely. So we can say, right, somebody if you ask you, right, what is this? So it is a part of also mechanics. We can add this to solid also, right? When you are studying the behavior of solid, we can say solid mechanics. We are studying here the behavior of fluids, right? So we can say fluid mechanics. So fluid mechanics is the study of the behavior of fluids either at rest or in motion, right? So when we are talking about study, so all the fundamental laws of mechanics will be applicable to it. So what are the fundamental laws? Conservation of mass, conservation of momentum, and conservation of energy. These three things we have to apply to understand the behavior of fluids, right? Either it is on rest or it is in motion. So in all the two cases, we can apply all these three fundamental concepts. And while we are studying the fluid, we can study what all properties changes are taking place in the fluids. So namely, when you are talking about properties, right? So properties are nothing but the, these are something quantities, right? Which talks about the physical condition of that fluid. So most familiar properties, usually we say pressure, temperature, density. Easily we can measure these, right? So pressure, temperature, density are the fundamental properties of any kind of substance, right? Maybe a solid in motion or solid at rest, or it may be a fluid at rest or motion. So we can say properties are any characteristics which defines the physical state of any substance is known as properties. So this is the branch which deals with the study of behavior of fluids either at rest or in motion. And I said that at rest, that study is called static, right? When it's in motion, we can either neglect the force causing that motion. Such kind of study is known as kinematics, right? When we are considering the force that causes that motion, right, then we say that kind of study as fluid dynamics. This point should be clear in your mind. You can note down these differences, right? There are three sub branches of fluid mechanics which are dealing with three states of these fluids, either fluid at rest or fluid is in motion. So, what are the applications area of fluid mechanics? Fluid mechanics is having wide range of application areas, starting from day-to-day domestic life to the industrial applications. So these are the various I have categorized. Apart from that, there are thousands application areas where you can use the knowledge of this fluid mechanics. So the first important area is biomechanics, which is basically required a lot of research, and a lot of research now being directed in the study of biomechanics. So particularly blood flow through arteries or veins can also be studied. All right, and you can also study the air flow in lungs, right? Flow of these fluids, right, in the veins. Household applications, right, particularly in piping systems, right, cold water, natural gas, or sewage water, right. So how to plan and how to install those piping systems, you can study, you can analyze based on the flow of the liquid, in what direction you want to flow. Based on that, you can install the piping systems, right. Piping and ducting network of heating and air conditioning systems, all right. Or you can go for weather forecasting, also meteorology and ocean engineering, chemical engineering. In mechanical engineering, there are various applications, right? When you are designing the compressor, turbine, pumps, you have to do the flow analysis, right? How effectively your flow is moving through the passage of blades, whether blade profile is disturbing the airflow, right? What amount of energy is getting lost, that can be minimized by studying the fluid flow domain in that particular cavity, right? Either external or internal flow, right? So there are various applications of fluid mechanics. Now, when we talk about the basic definition of fluids, as I said that fluid is a substance, right, which is capable of flowing. How flowing will happen? When something is flowing, what will happen to the molecules? Molecules will deform, right, when they are flowing. So fluid is a substance which deforms continuously or flows when subjected to a shearing stress or shearing force, right? So even with a negligible amount of shear force, it will deform, particularly fluid will deform. So it doesn't matter how small that shear stress may be, but it is having an inherent property of continuous deformation of fluids. That is known as fluids. So here clear you can see when you are talking about fluid flow, that means there is a presence of shear stress. When fluid is at rest, that means molecules are not moving. In that case, shear stress is zero. Shear stress is zero. So how shear stress develops basically between the two layers? You just look at this pictorial, presentation which is given here. So we can say this is a fixed boundary, or we can say a solid surface. This is one solid surface. We can say this is another solid surface here. So we can consider the case of fluid flow within the pipe. So pipe is having two solid boundaries, right? So this and this can be considered solid boundaries. Now fluid is moving, so fluid will have n number of layers, right? So if we consider the molecules motion, they will itself following some certain path while they are moving. So if we consider the case of laminar flow, where fluid layers are moving parallel to each other, so we can draw two parallel lines, right, for the fluid particle motions. So we can consider here the case, right, when flow is moving right over here. You can focus So when it's moving, what will happen? Molecules will be moving with the relative to each other, right? So between the molecules itself, there will be a generation of, force that is called shear stress, right? So that force will be acting on unit area of that molecule. So if we consider the total length of the flow domain, there will be a some definite value of shear stress which would be acting over the fluid domain. So we can say that whenever fluid is in motion, there will be a generation of shear stress within the molecules itself, which will cause the shear stress to be acting on entire fluid domain. If fluid is at rest, in that case, there will be no shear stress. Then you can say that what are the differences between the liquids and gases? Already you may be knowing from 10+2 concept that you studied there. All right. So when we talk about the liquids, liquids are very difficult to compress. You need to apply some external force to compress it. If you want to compress the water, particularly, you have to apply a certain amount of force on it. Then only you will be able to compress it. While gases are highly compressible, even with a negligible amount of pressure force, you can compress them easily. So one difference is that gases are highly compressible, while liquids are not too much compressible. You have to apply some external force, difficult to compress. Second, you can talk about the, this is basic, definitions, basic difference. Occupies a fixed volume and will take the shape of the container. And here, or you can say it is having a fixed volume and, shape is not defined. But here, no fixed volume. For gas, we cannot say it is a having certain volume. So no fixed volume. It changes volume to expand to fill the container gas or any container. If you want to fill, its volume will change. Third, most important difference between liquid and gas is that liquid always forms the free surface, right? But in gases, you will not find any kind of free surface. Why? Main reason is in liquid we will have a viscosity, right? Viscosity as well as surface tension. We will define that later on. All right. So viscosity and surface tension, these are the two important properties in the liquids. That's why they form the free surface. But in the case of gases, surface tension is missing. That will not be there. Because of that, gases never make any kind of free surface when they are filled in a container. So these are the main important differences between the liquids and gases. If somebody asks you, then if you want to address it technically, you can express in this term. All right. Next one is Newtonian and non-Newtonian fluids. So when we talk about Newtonian fluid, Newton is a scientist actually. He has given the theory for the fluid motion. As per his statement, he says that the shear stress developed in the fluid is directly proportional to the rate of shear strength. Rate of shear strength. So when you are removing the directly proportional, you will get a direct proportionality constant that is called viscosity basically here. So if you want to write the statement of Newton's, right, he has given like tau is directly proportional to the shear strength. Why shear strength is happening? Shear strength is happening because of the relative motion between the two layers. So if one layer is moving like this, another layer is moving like this, it will have a different velocity. It will have a different velocity. So some velocity gradients will develop here, right? So we can say the velocity difference between distance, we can say this as x direction, and if you say this as y direction, so this is a infinitesimally small, height perpendicular direction. Within that, there is a velocity gradient. So we can say here this is u1, and here it is u2, and due to difference of u2 minus u1, right, your velocity gradient is developing. That is du. And the rate at which it is developing is by the length. So du by dy, this is called as strand rate basically, or you can say shear strand rate. So when you are removing this directly constant, you are getting one constant term that is called viscosity here. So viscosity of fluid, and tau is called shear stress. So any fluid which obeys this law, or you can say any fluid whose behavior is represented by a linear line. If you are drawing stress versus strain, right, you will get a linear line, right, starting originating from 0 and going to any value, right. Such kind of fluid is known as Newtonian fluid. If any fluid which does not follow this law will be called as non-Newtonian fluids, right? Non-Newtonian fluids. So here some examples are given. So these are all the standard fluids, right, which follow this law, right? Tau is directly proportional to rate of shear strength. So example is air, water, oil, gasoline, alcohol, kerosene. These are the some standard fluids. All right. So now here we got the term called viscosity, right? So when we are defining this viscosity in a journal, we can say viscosity is something which is basically resisting the motion of fluid layers. So it will be acting in between two layers, right? So if you consider these two layers, between that, this viscosity will be acting, right? So viscosity is the internal resistance offered by the fluid to the shearing of its layer, or you can say it is the internal resistance offered by the fluid to its motion, right? It's called as viscosity. Viscosity. Whether this term is clear to you? Yes, please
Yes,
respond if
sir.
you are. Yeah. So viscosity is the internal resistance offered by the fluid to its motion, you can say, or you can say viscosity is the internal resistance offered by the fluid to the motion of its layer, right? So one layer will be moving, relative to the another layer at some different velocity. So now if I say, you will get some more idea. If I say this is a solid surface, right? This is a solid surface. So this is a solid surface, we can say. Now fluid is moving over here. So fluid will have a n number of layers, right? So these are the different layers. And they are keep on moving. And it is a open channel flow, right? We don't have any solid boundary here, right? So it is a open flow, and flow is going in this direction, we can say. So flow is moving like this. Now what will happen? The layer which is very closer to the boundary, right, which is very closer to the boundary will be moving at a very low speed, very low speed. As we move right away from the solid boundary in this direction, if you are keep on going, its velocity will keep on increasing because there will be less interference with the solid surface, because viscosity always plays vital role very near to the solid surface. If you are going away from the solid surface, effect of viscosity will keep on decreasing, if you are at very far away from the solid surface, you will not have any effect of viscosity over there. Viscosity will be there, but the effect of its will be very negligibly small. So the velocity gradient basically forming from the solid surface. So if I want to draw the velocity gradient for this kind of case, then I can draw, it is starting from the solid surface, we can say at the boundary, right, or a solid boundary, your velocity is zero, right? Zero. If you are moving away from it, its velocity will keep on increasing. So velocity gradient will be forming like this. So this is your velocity profile that you will be getting. Velocity profile. And between two layers, you can find out the velocity gradient. So in what direction your velocity is actually varying? It is varying perpendicular to the solid surface. Your motion is happening along x direction, but your velocity is varying in y direction. That's why we are getting this, shear strength or velocity gradient, right? Du by dy. Is that clear? So now one more important term will come here, that is called no slip condition, right? So I will be pointing out here. So I will say here no slip condition will exist. So no slip condition is the condition at which the motion of fluid attains, or you can say the velocity of fluid becomes equal to the velocity of the solid surface. So in our case, solid surface is not moving basically. So velocity of solid surface is zero. The moment your fluid motion, or you can say the fluid velocity becomes equal to the velocity of the solid surface, we can say the fluid has attained the no slip condition. So no slip condition only will be existing at the solid surface. If you are going away from the solid surface, there will be no case where you will get no slip condition. Is that clear? So no slip condition is the state at which the fluid velocity becomes equal to the velocity of the solid surface. Note it down, right in your notebook, because this is very important concept. You need to understand this clearly. So no slip condition. So Now, one more important, observation out of this equation is, as we got this as a constant value, right? Viscosity is a constant value, right? And which is a constant for a given liquid or for a given gas, right? So that means this velocity gradient that is developing, or rate of the shear strength which is developing between the layers, will not have any kind of effect on the viscosity. All right, that's why this term is coming here, right? Second point is mentioned here. The magnitude of the velocity gradient has no effect on the magnitude of viscosity, because viscosity is a constant value, right? Viscosity is a constant value because viscosity doesn't depend on the velocity gradient, but it depends on some other parameters. It depends on the temperature basically. If you change the temperature of this fluid domain, viscosity will definitely change. It will change drastically. It has some relation linear, sometimes it is having quadratic or cubic relation with temperature. We'll discuss it later on in the further topics. So, up to here, any doubt in this statement, Newton's law of viscosity?
No, sir.
Please don't accumulate the doubts. That's why I'm giving this much time. So this is very, very important law, and based on this, a lot of numerical problems will be asked. Okay, let's go for next topic. Non-Newtonian fluids. When we are talking about non-Newtonian fluids, anything, right, which is not following the Newton's law of viscosity, that means shear stress is not no more directly proportional to the rate of shear strength. Such kind of fluid is known as non-Newtonian fluids, right? Non-Newtonian fluids. Now, as we already seen, right? So somebody asked you to summarize and ask you to write some points about Newtonian fluids. You can say Newtonian fluid is something which follows the linear relationship between the shear stress and velocity, right? Because that tau is directly proportional to the rate of shear strength. So it is something which is having a linear relationship between shear stress and velocity gradient, right? Slope is constant because a linear line, and viscosity is also constant. But in the case of non-Newtonian fluids, slope will not be like constant. Right, slope may be like it may be a curve, right? It will not be a linear line. It may be a curved kind of thing between shear stress and your shear strength rate diagram. So here are the some examples of fluids, right, based on their behaviors, right? So if you look at the this line, right, I'm talking about this line. This line is exactly following the Newton's law of viscosity, right, where shear stress is starting originating from the origin and going to some value. So it is a linear line, right? So we can say any fluid which is following this line or this curve will be termed as Newtonian fluid. And apart from that, there is a deviation, right? This is a deviation, this is the deviation. These are all non-Newtonian fluid. And there is another fluid which is highly stressed. That means its shear stress will be starting from some definite value. So already there will be some inherent, stresses within that fluid, right? Highly stressed fluid. And from that, it will follow almost nearly, linear curve. Such kind of fluid is known as Wingham plastic fluid. So here example is given. So Wingham plastic is resist a small shear stress but follow easily under large shear stresses. So example, toothpaste, right, and jellies and sweat sludge. So these are some examples of Wingham fluids. Pseudoplastic, these are all non-Newtonian fluids, right? Non-Newtonian fluids, so viscosity decreases with increase of velocity gradients. So the moment velocity gradient increasing, right, gradient value, that is slope value, will decrease. When that is going to decrease, your viscosity decreases, right? So these are some example. Milk, clay, and cement comes under this category. And then dilatant, another is there where negative slope you may find, right? Viscosity decreases with increase of velocity gradient, right? That is called quicksands. So these are the some examples of the behavior of different kind of fluids. So it may be asked. All right. So you can go through. So here any doubts? Please respond.
No, sir.
Okay, please note down this point also, right? This is very, very important, thing. And when you are explaining this, you have to draw the diagram always, right, or mathematical equations to support your statement. Keep in mind. So next is properties of fluid. Let's we start the properties of fluids. So when we are talking about properties of fluid, it is any characteristics of a system which defines the physical state of that system. Is known as properties of fluid. Some familiar properties, as I already discussed, pressure, temperature, and volume and mass can be considered as familiar properties or fundamental properties. Other less familiar properties, these other means these can be derived from pressure, temperature, or you can say fundamental properties, right? These are viscosity, thermal conductivity, modulus of elasticity, right? Thermal expansion coefficient, electrical resistivity, and even velocity and elevation. So these are some other properties of the fluids. So one by one we'll see, right, what are these different properties. Let's start with some fundamental properties, that is called density or mass density. So density of fluid is usually defined as the ratio of mass of fluid to the volume of fluid, or you can say it is defined as the mass per unit volume. So when you are measuring the quantity of mass in a given volume, that is known as density. So based on the quantity of mass, we can say that it's a high dense or low dense region, or high dense solid or low dense solid. So it is usually represented by the notation rho. So this is notation, standard notation followed for the density. So the unit in SI, category is kilogram per meter cube, because it's the ratio of mass of fluid to the volume of fluid. So mathematically, we can say that density is defined as the ratio of mass of fluid divided by the volume of fluid. So mathematically, we can say mass always represented by the capital M, sometimes small m you can write, or divided by the capital V, that is called total volume. So we can say kilogram per meter cube. This is the unit for this. So now, every fluid or every liquid, right, liquid or gases will have their own densities, right? If you talk about the density of water, it is 1000 kilogram per meter cube. If you're talking about density of mercury, right, it is around 13.6 times of the density of water, or you can say 13,600 kilogram per meter cube is the density of mercury, because it's a very heavy liquid, right? Mercury that we are using in thermometer. And for water it is 1000. Like that, for different fluids, value of density will be different. Next one is specific weight or weight density. So specific weight or weight density is defined as the ratio of weight of fluid to volume of fluid, or you can say it is the amount of weight per unit volume of a given fluid is known as specific weight. All right. So specific weight, mathematically we can say weight of fluid divided by the volume of fluid. Now we can say weight as mass into, usually we say that mass into g, right? So mass of fluid into acceleration due to gravity divided by the volume of fluid. So mass divided by volume, already you know, that is called density, right? Density, and into z. So we can say specific weight is rho into z. It is denoted by the small w, right? This is the standard notation used for the specific weight. Don't make any mistake in this. If you are talking about total weight, then this will become the capital W. Capital W. So specific weight is small w is equal to weight of fluid to the volume of fluid. Clear? And the weight of fluid can be said as mass into acceleration due to gravity. And we know that mass of fluid divided by the volume of fluid is known as density of the fluid. So density into G is known as specific weight. Clear? Please note down this, because we'll be seeing some numerical problems based on this simple, definitions. Next one is specific volume, right, of fluid. So specific volume of fluid is defined as the volume of fluid divided by the mass of fluid, or you can say it is nothing but volume of the fluid per unit mass of the fluid. So we can define mathematically specific volume is equal to volume of fluid divided by the mass of fluid. Now this can also be written as 1 divided by the mass of fluid divided by the volume. So mass by volume is known as density. So we can say that specific volume is reciprocal to the density of fluid. So specific volume is denoted by the small v, right? Is equal to 1 divided by density of fluid. So if you know the density of fluid, you can easily find out the specific volume of the fluid, which is nothing but 1 by density of fluid. Is that clear?
Sure.
Okay.
Sure.
Okay. Yeah. Tell me. Okay, next one. Specific gravity. We have defined the specific weight. We have defined the specific volume. Now it is the specific gravity. So specific gravity, when you're talking about gravity, gravity term will come in which weight, right? Weight is equal to mass into g, right? There it was coming. So we can say specific gravity is defined as the ratio of weight density, or you can say, specific weight of a fluid to the weight density of a standard fluid. So it is the ratio of specific weight of any given fluid to the specific weight of the standard fluid. Now question will come, what is the standard fluid, right? Usually for liquids we consider water as a standard fluid, and for gases we always consider air as standard fluid. Note it down. For liquids, water is the standard fluid, and for gases, air is the standard fluid. So specific gravity is defined as the ratio of weight density of the liquid divided by the weight density of water, or you can say weight density of standard liquid. Or for gases, we can say it is the ratio of weight density of gas divided by the weight density of air. So thus, if somebody wants to know what is the weight density of liquid, you can multiply by the specific gravity and you can find out the weight density. Weight density. So weight density, when you're talking about weight density is called specific weight. Keep in mind, don't get confused. Is weight density is called specific weight. You can also write this in terms of mass also, right? Means density. In terms of density also, you can say density of liquid divided by the density of standard liquid, right? That will also known as specific gravity. So you can say here density of liquid is equal to specific gravity into density of water. Somebody will ask you what is the density of gas? Density of gas will be equal to specific gravity into density of air, will be known as density, or you can say specific gravity. So here weight density you're writing, you can also say that density of any liquid divided by the density of water. Clear? Here you can say density of any gas divided by density of air. It can also be written in this way. Specific gravity can also be defined in terms of density or weight density. Weight density is called specific weight. Don't get confused between the terminologies. Weight density is called specific weight, and mass density is known as. So for different, fluids, there are the value of, standard specific gravity. For water, it is 1, because for water density is 1000 and density of water itself is 1000. 1000 divided by 1000 is 1, right? For blood, it is 1.05. So you can say the blood density is around 1.05 times of the density of water, right? And for sea water, it is 1.025. Gasoline is 0.7 times heavier than the, your air. Ethyl alcohol is 0.79. Like that, for different, liquids or gases, there are different value of specific gravity. You look at the gold. Gold is 19.2 times, heavier than the standard metal, right? Right, and bonds, right, 1.7 and 2. Ice is also there, right? So for different, liquids and gases, there are different value of specific gravity. So you can say that specific gravity is a mathematical, or you can say it is a physical measurement of heavierness or lighterness, right? You can say it is heavier than or lighter than the standard fluid. So now let's go to the solve some numerical problems, right? So take this as an example, and let me start with. So this is saying that calculate the specific weight, density, and specific gravity of 1 liter of a liquid which weighs 7 Newton, right? That means what is given, they have given the volume as 1 liter, right? And its weight is also given, total weight is given 7 Newton, and you need to find out the specific weight, right, density, and specific gravity. So just you refer the formula of specific weight. Specific weight is the ratio of weight of weight of liquid or weight of fluid to the volume of fluid, right? That was the definition of specific weight. So we know the weight of fluid, that is the 7 Newton, and volume is given in liter, right? So 1 liter, usually we say that 1 liter is equal to around 10 to power minus 3 meter cube. 1 liter is equal to 10 to power minus 3 meter cube. So this is the volume which is given. Weight is given 7 Newton. So you can find out the specific weight very easily. Specific weight is equal to 7 divided by 10 to the power minus 3, or you can say the answer will be 7 into 10 to the power 3 Newton per meter cube. Is that clear? Like that you can find out the specific weight. If you are going for a specific gravity, how will you find out the specific gravity for this? Yes, any one of you?
Sir, standard liquid is divided by.
Leave the standard, one by one we'll go. So first we have find out the specific weight, right? Now you find out the density, right? Find out the density. How will you find out the density? Use the formula density is equal to mass divided by the volume. But problem is that we don't know the mass, right? Do you know the mass?
No, sir.
So mass can be
No,
calculated
sir.
from the weight, right? This weight is given. So W is equal to m into G. Clear or not? We can say W is equal to m into G. And G value you already know, 9.81 is the standard value. So you can find out the mass from here, right? Take this mass and put it over there, right, and find out the density. Do you have a calculator with you? So please solve and tell me the value of density. So from here, find out the mass and substitute over here. Find out the density. Yeah, do it fast. Are you facing any difficulty?
Sir, could you repeat it again, sir?
I am saying that you need to calculate the density. So density is the ratio of mass of fluid divided by the volume of fluid. I know the volume, which is given as 10 to the power minus 3 meter cube, but I don't know the mass. So mass of fluid can be calculated from the weight. Weight is given m into g. So I can find out the mass from here. Weight divided by the acceleration due to gravity. That value is fixed, right? 9.81, right? So you can divide 7 divided by 9.81, get the mass value, and put the mass value over here in this formula and tell me the value of density.
Sir, 713.5 kg per meter cube, sir. Density
700, 700,
13.5 kg per meter cube, sir.
good, kg per meter cube. Okay, so this is the thing. Now, once you know the density of this fluid, you can find out the specific gravity. So specific gravity formula says that density of liquid divided by the density of standard liquid, right? Standard liquid. So like that you can find out the standard liquid, as it is saying that liquid. So liquid means standard water, and for water density you know that is 1000. Density this you calculated, so you can say directly value is 0.713, right? Call specific gravity. Is that clear? Any doubt in this?
No.
So this kind of problem will come for 15 marks. Do you think this kind of problem actually deserves 15 marks? So those who have not done, you can look at here. Volume is given 1 liter, so we can say 10 to the power minus 3 as volume, and weight 7 Newton. So specific weight is weight divided by volume. So you got this value. And density directly can be calculated from that, mass divided by, or you can say specific weight divided by g, because we know the specific weight is equal to rho into g. If you don't know this formula, then you can go by this way, as I said. Find out the mass, substitute over here, you will get some value 713.5. so specific gravity is equal to density of liquid divided by the density of water. So we can got the specific gravity as well. So I don't think so you may have any problem in this. Okay, let's go for the next problem. Okay, I think there is only one problem. Okay, let's start the discussion now. So you have any doubt? Let's discuss now.